Thank you everybody for signing into this webinar. This will provide a little bit less of the fundamental science that we've seen in the previous webinars and more of an appreciation of how the technology is actually taking shape in the field and the performance that we're seeing to date. So to put this webinar in context, there have been earlier webinars that some of you may well have listened to and that are still available from our website or whatever. The first really dealt with the core concepts and the underpinning science. The second went deeper into factors such as the transport of the material through the soil, greater depth about the bioregeneration of the sorptive capacity, and through some of the early case studies, etc. This present webinar is going to provide just a short recap of the technology and the basics, but rather than give you 90% the same again and 10% new material, this is going to be 10% of some of the basics and then 90% new material. I want to then go through some of the usage statistics and some of the aggregate field performance to date. So this is now much more the bigger picture of what's actually going on in the world with this technology and how the technology is actually performing. I'm going to take this into some of the lessons that we've learned through this process, spend a few moments talking about the road ahead and what we see is coming next, and then I trust there'll be plenty of time for question and answer at the end. So to crack straight on with this, a little bit of background and some basics of the technology. Well, let me start at the beginning. It was probably back in about 2007 that REGENESIS started to look at the use of particulate sorbents to find and bind dissolved contaminants in situ. So almost 10 years ago. But the first thing that when we looked at surfactant modified zeolites, we looked at organoclays, we looked at activated carbons, and we looked at a raft of other potential approaches. And the key thing that we found was this. Activated carbon and other sorbent particulates do not disperse in the aquifer. Granular activated carbon particles are about 1 millimeter in diameter, about 1,000 microns in diameter or thereabouts. Powdered activated carbon, even when it's milled small, the actual powder, even though it might look like the material in a photocopy toner, the particles are around about 40 microns in diameter, but once they're in water, they will agglomerate again up to about 1,000 microns. So what you can see in the image on the right here is a sieve, a field sieve, with a small mesh size and with the mixed up carbon and water particles not passing through the mesh, even though the mesh is substantially larger than the carbon particles themselves due to agglomeration. This is significant because the typical pore throat diameter in soils for silts and sands is of the order of 5 to 30 microns. So we're really pushing it with 40 microns in diameter of the actual particle. But if we get agglomeration up to 1,000 microns, then clearly we're going to see blockage and clogging, and we'll be challenged to get the material dispersively any distance from the injection point without soil parting or fracking. I'll talk a little bit about that maybe in some of the later slides. So the timeline of development of the reagent, the R&D stages, well, they're still ongoing as we go on with different ancillary research for betterment, improvement, etc., and the questions that are coming back from the field or from client meetings. From about 2007 to 2013, we were going through R&D stages for this. Field beta tests then with the technology, and most of that early research was how can we actually overcome the clumping, how can we get the dispersion of the material without compromising sorptive capacity, etc., etc. The field beta tests then went forward with the formulation that we're presently using. There were some others that we tried before that were not as successful in the field reliably as we saw in the lab, and they didn't get past the beta phase. The present formulation was beta tested from about 2013 to about 2014. It worked well, it worked reliably, and so its commercial launch under the trade name PlumeStop was undertaken about 2 years ago at the Chlorinated Solvent Conference in Battelle up in Monterey. Commercial applications followed soon after that. They really just shot on behind it like they were straight out of the starting gate, out of the barrel of a gun. And it's really those that we're going to be reviewing in this presentation. So what is the reagent? Well, in the simplest terms, it is a highly dispersive, injectable sorbent and a microbial growth matrix. The same material as the sorbent and the growth matrix. This isn't a mixture of two materials here for two different functions. One material, two functions. The basic point is that the sorbent will provide a rapid drop in dissolved phase contaminant concentration and therefore immediate risk reduction. There's no destruction going on here. This is simply capturing the contaminants out of the mobile phase in the groundwater and holding them on the sorbent surface. So the risk reduction, the exposure risks, the impacts to groundwater are dropped right down, but nothing's been destroyed. That's where the other component of its function comes in, the microbial growth matrix. There will be accelerated biodestruction of the sorbed mass on the carbon surface and in between the carbon particles where the material is held. I won't go into this in detail in this presentation because this was one of the principal themes of the previous two webinars, but if there are questions time at the end that you want to go into that, then perhaps there will be time. The basic idea is that bacteria will grow very well on carbon. The contaminants will partition, sorb reversibly into the carbon. In other words, it's not a binding technology, it's a sorbing technology. They will remain available for biodegradation, like a biogac, but their local availability is much higher for the bacteria growing on the carbon. So the conditions for degradation, the bioavailability is better. So long as the right electron donor and acceptor balance is there and the conditions are right, then we'll get good biodestruction post-sorption. This enables much lower targets to be secured because with the contaminants concentrated onto the carbon, even if they've been in a diffuse plume in solution, their local availability is such that the microflora can thrive and the degradation can proceed, even though it might have been under oligotrophic conditions, stalling conditions if you like, in the wider water before that. What is the material? Well, physically, it's colloidal activated carbon particles. They're about 1 to 2 microns in diameter. It's about the size of a blood cell. It's about the size of a bacterium. The material will suspend as a liquid, like blood, which is a colloid. It has a huge surface area, not just because the particles are small, micron or 2 microns in size, but because the activated carbon itself has a very large internal surface area. We're talking something like 800 to 1,000 square meters per gram of material. But it didn't take research from 2007 to 2013 to figure out how to grind carbon up really small. The real challenge was how to actually get the material to overcome the clumping that was going on, and moreover to do this in such a way that didn't mess with the sorptive capacity of the carbon. There are a bunch of ways it can be done, but that compromises the sorptive capacity. How can it be done without compromising the sorptive capacity? Well, several hundred column studies later, we came up with, oops, I pressed the button twice, proprietary anti-clumping and distribution supporting surface treatment, which is the core innovation really of this technology, that enables the carbon to essentially behave like it's a liquid. This is the core innovation, and it's this that enables wide area, low pressure distribution through the soil matrix without clogging the formation, without the particles aggregating and getting clogged up in pore throats, and to actually get the material effectively through the formation to where we need it to do its work. So the basic concept then is this. We can inject it or simply gravity feed it depending on the circumstances and the setting in question. We can inject it at low pressure through a well or a direct push point or a variety of other packer stinger assemblies or whatever it may be that's pertinent to the formation. We can get a wide distribution of the PlumeStop through liquid flow. It will then coat the formation. What we're looking at there is a micrograph of the little rough squares that you can see there of PlumeStop particles on top of a sand particle. We'll look at some better pictures further on. But the injection's over now, the material's in place, it's coating the soil formation. We'll get contaminant absorption into the PlumeStop carbon. Bacterial growth will soon follow because they now have a surface which is replete with their favorite food or contaminant. There'll be the accelerated biological degradation simply through the increased local bioavailability of this. This is information from the first of the webinars. The absorptive sites on the carbon can then be regenerated so that they can capture more material. That's data from the second of the webinars. This means that with further influx or from up gradient or back diffusion out of lower permeability parts of the formation, we can then capture more contaminants, and then around and around and around this loop we can go without the PlumeStop carbon itself being consumed in the process. So reagent distribution is core to this. Securing the reagent distribution was exactly what we were trying to do. This image really remains, I think, one of the most graphic illustrations of this. We have two columns of fine silty sand. Into the one on the left we're going to put PlumeStop, and into the one on the right we're going to put powdered activated carbon. Exactly the same amount of carbon, exactly the same volumes. The difference is the treatment. We're going to open the tap at the bottom of the column. The columns are about 18 inches long, about 2 inches wide or thereabouts. And we're going to see how the flow progresses through gravity feed. It looks something like this. The columns are being topped up with equal volumes of water as we go, so that the actual volume of liquid is the same. But what you can see, the PlumeStop has simply just drained straight through the column and has left a coating. The carbon has agglomerated and clumped up in the top inch or so of the column, as we'd seen in that earlier sieve. So essentially this is the difference that we've been trying to secure with the surface treatment. To give an idea of what this looks like over field practical distances, if I can get this animation to run, this is a 16-foot column in our lab. I'm just turning it on now, and you might be able to see, depending on your monitor resolution, ching, there comes the PlumeStop out of the top of the column. You can see the demijohn on the right going down, the demijohn on the left going up, as the material simply just flows through. This is being driven by that little peristaltic pump you can see on the right. And this goes on through a bunch of pore volumes. Then we push some chase water through to see if we can actually wash out the PlumeStop. There's some chase water going through. And I think I'm going to stop there because this just goes on and on and on. There we go, there's a bit of water coming through. So essentially we could see in this the front of carbon progressing through the column by flow rather than fracture. On the third image we can see the column full of carbon, and on the last image we can see the residual coating after we've put through about 9 different pore volumes at an equivalent seepage velocity of about 35 kilometers per year. So even under extensive flushing, the coating that's left sticks and sticks hard. A more graphic illustration of that is that if you get some of this material on asphalt, for example, even a jet washer struggles to get it off on day one because it will flow, but it will leave a coating. When we actually look at the sand particles from these columns, this is what they look like through electron micrographs prior to the PlumeStop application. The scale bar there is 50 microns. After the PlumeStop application, scale bar now 20 microns, you can see the sand particle, but you can see this rough coating of the PlumeStop particles on top. Everything looks the same color because it's the type of microscopy that was being used. Here's another image. Again, you can see the large sand particle, and you can see the PlumeStop coating on the surface. This would be sandy color, this would be black if we were looking at it with an eye. We're not, we're looking at it with electrons. But this is the basic idea of the coating that we get. Onto this, between and among the particles, a biofilm will grow. These are some images of different biofilms. The scales that we've got here are 0.5 micron each. So if you can run the exercise in your brain, you'll be able to work out that these are about the same type of size as the particles. So the idea then is that we can push the PlumeStop out through a sort of dispersive flow through the formation rather than fracturing it through. That means that any monitoring well present is going to get pretty much what is going through the groundwater. No real life situation is going to be a sphere like this, but this is a cartoon to really illustrate that we're getting dispersive flow rather than fracture flow. So rather than fracturing the carbon through in a discrete seam, as we can see in this image here, so sort of pure carbon, perhaps 1/8 to 1/4 of an inch in a seam that's pushed the soil apart. Rather than that, what we're actually going to see, and this is again from the field, are the PlumeStop particles flowing around the sand particles dispersively and just coating the formation. So that's really the flow-in-placed liquid activated carbon in contrast to fracture-in-placed powdered activated carbon. There's a place for each technology. What this is meant to clarify is the difference between fracture-in-placed carbons and flow-in-placed liquid activated carbon, or PlumeStop. If we expand up the pore throat between soil particles, here's a soil particle, here's the pore throat, then what we will see would be all the little particles of the carbon on the surface here with the red contamination soaked into them, that's hence the colouring, and then the bacteria growing on and between them. These are those little yellow coccoids that we can see. So essentially that's a cartoon of the type of micrograph that we're seeing here. So enough of the basic background. Many of the questions that we've had of the technology have been along the lines of these. What about distribution in low permeability zones, clays, silts or whatever? What about the contamination in clays? How on earth are you going to push any liquid through a clay? What's your injection radius of influence? These different questions come up in a variety of different forms, so let me address them in a couple of slides here. So here's an illustration, a cartoon of a contaminated formation. The pink color is contamination. Let's presume groundwater is flowing from right to left. Here's the phreatic surface about up here. Here's our bedrock. We've got higher perm zones with the contamination going through them, and we've got lower permeable zones like clay with very little contamination in. So basically the contamination that's advecting through this formation will transport through the higher permeability zones. These are going to be the principal flux channels. As the material passes through the flux channels, there will be progressive contaminant diffusion into the lower permeability zones. These are the areas that are going to give us residual storage and are going to play the back diffusion for any type of pump and treat or many other different types of technology. These are the storage compartments. There's not much flow there, but there is diffusion of the mass into them. There will be limited or negligible contaminant penetration deep into the competent low permeability formations, whatever they might be. The diffusion will only actually go so far into these sort of fringe zones above and below the principal flux channels. So when we put PlumeStop in, remember groundwater is going in this direction, PlumeStop can flow into the groundwater at low pressure. It's possible to apply it at just a few PSI depending on the formation actually called for in the site work, and in some cases it can gravity feed in. The PlumeStop itself will also flow, like the contaminant, through the principal flow channels, and it will leave a coating on the surface of these as it moves through. How far will it move? Well, my favorite analogy is still to imagine dropping a bead of ink onto a sheet of paper, tilting the paper and watching the ink roll over the paper. The bead of ink is going to roll over the paper and it's going to leave a coating. The coating is going to be stuck. The bead will keep rolling until there's no ink left because it's coated the paper. It's pretty much the same story here. How far will the PlumeStop move? Well, it depends what volume you put in and what degree of stickiness there is from the PlumeStop to the formation material itself. So like the bead rolling over the paper, the PlumeStop is going to roll over the surface of these soil particles until basically the PlumeStop's all being used up. So it will coat the principal flux channels. What then happens is that contaminant mass back diffusing from the lower perm zones is captured by the PlumeStop in the flux channels. And so in this manner, the low and the high permeability zones are addressed. The high permeability zone is addressed because as contamination flows through it, it's replete with PlumeStop, it just gets captured. The low perm zones are addressed because as this material back diffuses out again, and it will back diffuse out because this concentration in the groundwater is low now, so the diffusion gradient is reversed. As it back diffuses out, it's going to get captured. The PlumeStop therefore flows like water, leaves a coating. The distance that, or radius that it progresses therefore depends on the volume injected and the amount of carbon that's injected in that volume. And this is dialed into what is appropriate for the particular site and revised through the field testing process, which I'll come on to in a minute, and the actual contaminant flux capture requirements. Field application then is really all about ensuring placement in the flow zones and making sure that these flow zones are adequately targeted and not missed. What we don't want to do is have, say, a top-down injection at, I don't know, 2 or 3 foot spacings that misses an important flux zone, which may actually only be a couple of inches in diameter. So it's important to ensure that the flux zones are targeted. An efficient, effective cleanup is all about accurate flux zone targeting. Some of you may have heard a webinar last month on that from my colleague Craig Sandifer. By the way, what this looks like in practice is something like this. Let's go away from cartoons and into field images. Here you can see a core that's been split open, and you can see the dark coloration of the carbon in the higher perm zone, and then little to no carbon actually in the clay that spans that on either side. So that's really what real world looks like. In this case, this is the flux channel, this is the storage compartment from back diffusion, and this is hardly impacted at all. So what about usage of PlumeStop then? Since it was launched in 2014, how much has it been used? Well, the map looks something like this. Since the beginning of this month, there's probably another half dozen dots on the map. These are the sites on which PlumeStop has been applied. There are now more than these as well. But when I put this particular slide together at the beginning of July, that's what it looked like. What you can see, and the reason there's such a density around the Midwest, is essentially we started rolling it out from the Midwest, and we've been progressing out from there since. So the Midwest has actually had more time putting this in the ground than other parts of the States. But overall, we're on something like 66 commercial sites at this point of time. Now, I gave this basic slide at Battelle back in May, and at that time there were 50 sites. So since Battelle in late May, we've got about another 16 sites. So they're going in the ground at this point of time at a rate of about 1 to 2 per week. So no, things are very busy. We're in 23 different states. We're in 7 different countries. These are the states. I'm not going to read them all to you. You can read them as we go. Next time there's one in Puerto Rico. I want to go down there too to see it being injected. I think it's important. Within countries, we're in the USA, Canada, Italy, Belgium, the UK, Sweden, and the Netherlands. And we have something like another 300 projects which are in the pipeline going through the various levels of design, question and answer, scheduling, etc., etc. So the curve is getting pretty steep, and we're very excited about it. Of the sites that we can see here, 26 of them, 39%, are at the pilot scale. 40 of them, 61%, have progressed up from the pilot scale to the full scale. Now, I haven't double counted sites. If a site has gone from pilot to full scale, a pilot then a full scale application, that's still one site. So the field experience is actually more than 66 sites. It's 66 sites plus the betas, plus the pilots, etc., etc. In terms of what we've treated, well, interestingly, we're bang on even Stevens between hydrocarbons and solvents, or in a more general sense, aerobically degradable contaminants and anaerobically degradable contaminants. We're on about 31 for each. That doesn't add up to 66 because 4 of the sites had commingled plumes with no real dominant class. Other contaminants of note that are in this field set are PAHs, Freon, MTBE, tertiary butyl alcohol, chlorobenzene, and there are a range of other things which we're exploring and looking at, such as different explosives, such as other chlorinated organics or non-chlorinated organics. The list goes on and on. The experience is growing very fast now. So what about the performance with these? Well, 66 sites is not practical for a webinar if I give 66 case studies. So to try and turn this into something which is comprehensive but digestible, ran through an analytical process which basically, and I'm not expecting this to be legible to you all, looked at all of the sites and all of the data that we've got, pooled everything we could find, and what you can see on here is a color coding between blue and white. The blue points are the wells in the zones where we would expect to see an influence of the PlumeStop, either because we're in an effective timescale from the point of application, or we're in the treatment grid, or whatever it would be. The white points are just other wells which are on the same site outside of the treatment zone and where we wouldn't expect to see PlumeStop. So we've looked at the data that we've got across these. Some are new projects, some are old projects. We've pulled all of the data that we've got and run some basic analytics. For this exercise back in April, May, we had access to data from 24 of the sites. Remember, these projects are being run by the consulting firms or the engineering firms, and they are not always at liberty to share data with us. But of those that could share the data with us, we had 24 sites worth of data, which are summarized here. So we looked at wells within the expected zone of impact, as I've mentioned, and we looked at the total contaminant reductions over time. And we created performance histograms of the full data set, basically showing the initial capture and then the stability of this capture from the time of application to date. And what the histograms look like is something like this. So here is the first capture histogram. We've got frequency, the number, the proportion of the sites up on the y-axis, and then we've got the percentage reduction in 5% bands along the bottom. So what this is basically telling us is that between 96 to 100% is that something like 60 to 70% of the sites and the data points were reduced between 96 and 100%. It's hard to refine that up above about 96% because in many cases we're getting to method detection limits, and if it's simply saying less than 5 micrograms per litre or less than 1 microgram per litre, it's not possible to say whether the actual capture was 99.999 or whatever it may be. So the top bracket is 96 to 100. And we can see that in some sites nothing happened. I'll come on to that. In some sites we got moderate performance. In most of the sites we got quite significant performance. Up in that top bracket we've got, among the anaerobically degradable species, chlorinated ethenes, chlorinated ethanes, we've got Freon 11. Of the aerobically degradable species, we've got TPH, BTEX, MTBE, PAHs, chlorobenzene, and some of the usual suspects, all up in that 96% bracket. What these statistics are telling us overall then is that something like 65% of the points were reduced to below MDL, so greater than 95% reduction within the first 90 days, within the first few monitoring rounds. 70% were reduced by an order of magnitude within the same period. More than 80% reduction was achieved by 90% of the applications, and only 10% of the total applications showed less than 65% capture or reduction within the first 90 days. We'll talk about that in a moment. What about the stability of those points to date? Well, this is where the corollary, the inverse of that curve comes in, and it looks something like this. So this is a measure of the capture over the full data set that we had. So the longest of these is 738 days from application. The average is about 200 days. It's getting a little longer now because this was April, but cranking the data set is an exercise, and I've not done it a second time for this talk. What we can see along the x-axis is the percent increase post-initial capture. What does this mean? Well, this is how much the concentration has gone up after the initial reduction as a fraction of the baseline. So if something drops from concentration X down to whatever it may be and then rebounds back up to concentration X, then that's going to read as 100, because 100% of X is 100% of X. If it's dropped right down and then drops up by 10% of the initial concentration, it's going to be somewhere down here. So what we can see in this particular image is that 70% of the wells that we had access to showed no change after the initial capture, or indeed the concentration dropped further. And 85% of them remained within 10% of the initial result. The remainder, bar one, were pilot tests. So most of these along here are actually pilot tests. It's not therefore surprising that we're seeing some of the concentrations coming up again, because the whole purpose of a pilot test is to calibrate the main performance, the main project, and therefore applications around about what we think the boundary condition is going to be much more informative for a pilot test than simply overdosing the thing, getting a fantastic result, but then potentially overdosing the entire project and using a bunch of carbon and therefore money that we didn't need. So this basically is an indication of tests doing the calibration exercise that they're required to do. So let's just take a moment to look at that. The blue is the initial capture. The red is the stability of that. I don't know about you, but I can't think of any other technologies on the market at the present point of time that have performance statistics like that. Thermal perhaps does, but you can't inject thermal at low pressure over a wide area with a geoprobe rig. So it's these types of data that are certainly leaving us at Regenesis very excited about the technology, and this is being reflected in the repeat usage we're having with different consultants and engineers in the professional fraternity across the States and Europe. We've got time to drill into this a little bit deeper, so I'm going to go into some of these a little bit more. Let's take a look at this awkward one down at the bottom. How come nothing happened here? Well, we looked carefully at it, and in this case, this one that showed no reduction at all was, we found, was an application into demolition rubble, historic foundations of buildings, multiple refusals. So what we basically, there was no recorded PlumeStop influence at all. What we believed happened here is that the material that we put in basically got lost in a void or a rubble channel or a pipe run or whatever it may be, and just channeled off in one direction and didn't actually hit the monitoring well. Or indeed it could be it was a monitoring well artifact. Significantly, on the same site, the other wells performed something like this. So this is what I would really consider the material just getting lost down a rabbit hole somewhere rather than dispersing through the formation. The other awkward one down there had excellent bio results. This was a chlorinated solvent treatment. We put an electron donor in there as well. But we saw no PlumeStop influence in evidence. When we looked more closely at the history, we found that the well was in a zone of historic oil-based electron donor. What we think happened was that the null PlumeStop result was due to competitive sorption of the PlumeStop onto lingering oil residues, or just picking up some of the oil and therefore not having any capacity left for the solvents. Other wells on the site were still not in the top bracket, and we think that's down to the oil as well, but they weren't quite as extreme. They're right up there. Other wells, here's a site where we got moderate, very good capture for the red and the green here. That's PCE and TCE. Relatively poor capture for the DCE. That's really because this well was at the upgradient periphery of the site, so it's got a very shallow PlumeStop dose, a very light PlumeStop dose. and because the sorption is better for PCE and TCE, we've got good capture of that. Because the sorption is less for DCE, the proportionate capture is less. So we've got maybe 90% of PCE and TCE, lower KC of DCE is showing that we're sort of at the boundary effect. This is the same site, but with, again, now we're at the edge of the plume rather than just an upgradient periphery. It's a lot better, but really the pay dirt is here. Where we're in mid-plume, we've got the full dose as prescribed, and you can see that we've got capture of all of the contaminants to below the method detection limits, which are these that are flagged up here. So this shows how there's a clear correlation between the amount of carbon that's put in and the actual capture dose that you've got. It's not all about capture, it's about capture and bio, but in these data I'm looking at the capture component. Here's another one. This site was in North Carolina. It's a solvent site, and again you can see the solvents just getting knocked down. There are actually data here and here, but you can hardly see them because they're close to the detection limit. But as the bio starts to kick in, you can start to see some of the daughter products just pick-a-booing into the dissolve phase, but most of the degradation is going on the carbon at that soil, at that carbon-water interface. This one is a filling station site, so we've got benzene, gasoline, that's the big gasoline spike there, xylenes, ethylbenzene, etc. The gasoline is knocked down to detection limits. Those are the detection limits plotted there rather than residual gasoline. If I take the gasoline out, this is what the concentration drops look like. So here's the BTEX getting knocked right down. Trace of benzene here, it's gone for the next sampling events. What I'm particularly interested in this one is MTBE, which doesn't soar particularly well to carbon, but the dosage was dialed in appropriately on this site so that the MTBE was captured too, and we've got MTBE captured to below the MQLs. Bio proceeds thereafter. Again, that's another story principally from the second webinar. Here's another example from the top end. This is more of what we're typically used to. Concentrations quite high for a PlumeStop site. 10 is normally the point where we cease to feel comfortable with using PlumeStop alone and might have an ISCO front end or whatever it would be. But here we've just dosed up and we've knocked the solvents right down straight away. And another one for BTEX on a site over on the east coast. Again, you can see these are the more typical PlumeStop results that we would be familiar with. From the long term, I mentioned that all bar one of these here were pilot tests. This one was the one that was in the zone of historic oil-based electron donor applications. Bio results were excellent, the capture was less. It looked something like that. So again, you can still see the concentration drop right down, but not as much as if we got the full complement of PlumeStop matched up appropriately with the massive contaminant we're trying to capture before we biodegrade it. Here's another one. These are more typical of what we've seen. This one's one of the longest running ones. It's actually now at 30 months, and it looks the same. This is principally PCE here that's dropped down to 0. And then absolutely nothing has been seen for the first 18 months until we start to get little sniffs of daughter products, vinyl chloride, which sorbs least, showing up. These are still very low concentrations. We've seen no other daughter products, presumably because they're sorbing better. There's no history of daughter products here on this site, so these aren't coming in from upgradient. These are from within the treatment zone. But this is typically what we'll see for most of the applications. Same biodegradation, only much, much quieter. So what lessons have we learned through all of this? Well, the first lesson that I'd like to single out is this. It's not about how much carbon you can get in the ground. It's also not about how far away you can see that the carbon you've injected has moved. What it's really about is how much of the contaminant flux you can intercept. So what I mean by that is that getting the material into the ground is actually quite easy. It flows like water, you can inject it like ink, but ensuring the optimal distribution is the art, making sure we're targeting the right dose against the right flux channels so that we're capturing the contaminants and getting them in the state that the biodegradation can follow, whether it's by natural attenuation or whether by its biostimulation plus bioaugmentation, and each may be appropriate on different sites. So bad, therefore, is where we get more than 90% of the placement intercepting less than 10% of the contaminant flux. Those were some of the sites we saw in building rubble, for example. Good is where we get 90% of the placement intercepting more than 90% of the contaminant flux. That's accurate targeting. So ensuring placement in contaminant flux zones is key, and it's an integral part of ensuring the success of applications. And it's wrapping this up as a package, therefore, is our strategy for PlumeStop. We will apply and sell and apply the PlumeStop as one service, simply so that we can get the material into the place that we need, and we can use the full experience that we've got from the growing number of in on those. We've got field teams in Europe. You can see the van going through the Alps on the left, and we've got field teams right across the States. There's quite a number of them now. The pre-application flux zone verification is a process that we'll use to accurately map where the flux channels are, and we'll do that with cores. We'll do that with hydraulic profiling kits. We'll look at how appropriately sorted or how sorted the material will be. We'll look at the fines contents and a whole range of things that will be done with this. It's quite an elaborate process. I won't go into it. Craig gave a webinar on that last month, which is available. But the basics of this, it is a pre-application field verification of the remedial design parameters. In other words, a high-resolution identification of contaminant transport strata. We undertake it directly ourselves, and it enables accurate placement of the reagents for maximum flux interception. Why is this necessary? Well, it's necessary because site investigations typically and rightly focus on liability and risk assessment. So their emphasis is commonly on contaminant identification, plume dimensions, and migration pathways. That is a different set of objectives from flux zone verification, which is all about efficient reagent contaminant contract, emphasis on identification of principal impacted strata, contaminant mass distribution, and reagent delivery. A lot of the kit used is the same. It looks like a site investigation, but it's different. It's a bunch of different questions being asked. Some of the folks listening may be long enough in the tooth to remember when contaminated land investigations were simply geotechnical investigations with some samples taken. Well, you could get something of a picture from that, but not nearly as much as you'd get if you did a bespoke contaminated land investigation. And this is the same principle for flux zone verification. We typically do it about 4 to 6 weeks ahead of the planned application. This allows time for data analysis and any refinement of the design. The outcome of this has been very interesting. When we reviewed the total that we'd done earlier this year, we found that 80% of the tests encountered unanticipated results. We found things that had not been evident from the risk-based site investigation. And as a consequence, 2/3, almost 70% of the preliminary designs had to be modified or refined to ensure the success that we would be looking for. But here's the kicker. 80% of the design changes were cost neutral. It was simply a matter of maybe changing one type of application technique for another, changing the dose and the balance, little tweaks of the approach. So this really comes with the strategy that we're aspiring to, which is 100% PlumeStop success, so much so that if the circumstances are right, we'd be happy to talk to you about guaranteeing the results or performance-related payment structures site by site. So where's this taking us? In the last 5 minutes, what would I like to share with you? Well, this is really where we're looking at now, not Route 66 in Arizona, but what we're looking at specifically now, one of the areas of considerable interest is the integration of PlumeStop with fate and transport models. Now, I could talk at length about this, and perhaps it'll be the theme of another webinar in the future, but briefly, one of the things that we've done is taken the simple biochlor model, and we've added a component to this, or more specifically, Professor Arturo Keller of University of California, Santa Barbara has added an extra component or routine to the biochlor model that incorporates the PlumeStop addition itself. So as well as the natural FOC that may be there, there's another set of inputs where we can put in the dose and the distribution of the PlumeStop, and then we can look at what that will do to the plume. We can use this to play a range of tunes either on the design or exploring the ways that fate and transport might be modified. So essentially, the point is this, that through the ability to dispersively flow activated carbon into the subsurface and coat it, we can basically engineer the desired retardation factor into the transport zones of a formation. We can engineer the desired retardation factor into the transport zones. That means that with this model, for example, or any other model, that's another story, we can dial in the desired outcome. Let's just change this parameter until the plume is stopping where we want it to stop or slowing where we want it to slow or whatever it would be while the groundwater moves unimpeded. Let's explore the different design options. One barrier, two barrier, fat barrier, thin barrier, two shallow, two light ones, one heavy one, whatever it may be. We can look in the different, we can put in the different options, we can explore the design options, and then basically when the model is telling us the basic design that looks about right, we can turn it into reality out in the field. That's really what PlumeStop's doing. And what this takes us to is another exciting area that certainly was, in my experience at least, one of the big themes at Battelle a couple of months ago in Palm Springs. And that's these babies, perfluorinated compounds. I've used the two principal celebrities, PFOS and PFOA, in this image, but there are some 6,000 others as well. For those who aren't familiar with perfluorinated compounds, they are resistant to just about anything that we throw at them, and they are widely used in aqueous film-forming foams, pizza trays, Gore-Tex, Teflon, a whole range of different things. There's a lot of them in the environment, and they're becoming increasingly appreciated as a problem. They can't be, there have been no field examples of their chemical oxidation, they're not amenable to bio, they can't be air stripped, which doesn't leave an awful lot of treatment options other than pumping and treating, capturing them on carbon and incinerating the carbon. What we've looked at, therefore, is the degree to which PlumeStop interacts with them. And what you can see here in the image on the left is the sorption isotherm, Freundlich isotherm, of PlumeStop on PFOA, and similarly the Freundlich parameters of PFOS and PFOA compared to PCE for the amount of PlumeStop that would be necessary to take, say, 5 ppm down to about 0.05 ppm, 5 ppm to 5 ppb. And really the sorption on PlumeStop is rather favourable. As you can see, we need about half to a third of the amount of PlumeStop to take out PFOS or PFOA by sorption, no degradation here, these things don't degrade, than we would for PCE. And PCE we can take out very, very easily. A lot of the results we've seen in the previous part of this presentation were PCE. To give an idea of this, if we had a plume that's rolling along of PFOS or PFOA at about 100 micrograms per litre, and we want to get it down to half a micrograms per litre, actually that's about 10 times higher than the concentrations that we typically see out there now. And let's say we've got a fast seepage velocity of about 150 feet per year. PlumeStop barrier, average dose, average width, single line of points, for example. Based on single components, there'd be enough sorptive capacity there to take out 12 years of this plume, or 11 years for PFOS, compared to about 3 years with PCE. If more capture is necessary, then it will be possible to add another barrier. And sure, I appreciate this is capture only, but if that's 12 years of a plume being held on site rather than expanding into a neighbourhood, or 12 years of operating a pump and treat system, then there are some cost benefits to be considered within this. Essentially, therefore, the concept is really this. We're not eliminating the problem, but we are certainly stopping it spreading. And all the parents listening to this are going to know what I mean. So I've covered a lot of things. I'm getting close to the Q&A time. Before I get on to that, of all the different take-home points that may have come from this presentation, if I was going to reduce these to one particular take-home point, What would I single out? Well, I think it would be this one. We now can turn the subsurface into an activated carbon filter. Rather than pump out water and pass it through carbon, we can disperse carbon through the formation and capture the contaminants in the groundwater. We can do it to engineer plume dynamics, or we can do it to capture the contaminant and then biodegrade the captured material in the subsurface. So it can be for capturing and focusing bioremediation, getting to stringent targets much faster, managing back diffusion. Remember, the PlumeStop doesn't get consumed, so as long as the biostatus is adequate for the regeneration, the contaminant will keep getting captured, keep getting degraded, freeing up space for more capture, and this will go on and on and on, we presume, for decades. But we can also use this approach to passively engineer plume dynamics. This gives us an opportunity for long-term migration control without pumping while the groundwater flow remains uninterrupted. Essentially, therefore, the retardation factor in our models is now an engineering variable. Thank you very much.
All right, thank you, Jeremy. That concludes the formal section of our presentation. So now at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a few reminders. First, you'll receive a follow-up email with a brief survey. We do appreciate your feedback, so please take a minute to let us know how we did. You will also receive a link to the webinar recording as soon as it is available. And again, we'd suggest that you download the PlumeStop FAQ document in the handout section. If we do not answer your question during the webinar, it might be because it is already covered in the FAQ. All right, so let's circle back to the questions. We have a lot of questions today, so if we run out of time before we get to your question, someone from REGENESIS will make an effort to follow up with you after the webinar. Okay, so let's see here, Jeremy. First question is, because efficacy is directly related to the ability of the material to disperse, does this preclude its use in fractured bedrock environments?
It does not preclude its use, but it makes the project a lot harder. It depends on the type of bedrock. If it's saprolite, it's going to be a lot easier than if you've got a karst formation or something like that. So the PlumeStop is going to flow and move freely. We had a fracture site go in the ground in early May, I believe. We had abstraction about 100 feet away, and it was certainly easy enough to get the PlumeStop to appear in the abstraction point 100 feet away. But the real question is, how much of the contaminant flux have we intercepted? Based on the design, we believe we've done a good job based on current knowledge, but it's going to be interesting to see on that site how much has actually been secured. We only went in May, the early data are good, but to answer the question, fractured rock applications are not precluded, but depending on how complex the fracture system is, how many dead ends, how many blind alleys, how many drain holes there are, it can be challenging. If the fractures are very fine and very hairline, a fractured granite perhaps, then you may want to think twice about putting the material in, because even though it is colloidal, it is a solid, and there will be a point that there may be a clogging. So all of these things have to be looked at. So that answer overall is a cautious yes to fractured rock. It depends how complex it is, but it's going to be a much harder project than most alluvial applications.
Okay, all right, thank you. All right, so let's see here. Next question is, how do we know that the high reductions are not just representative of what's in the well versus what remains in the formation?
That's a very astute point, and would that question were asked more widely across the industry. The answer is that the real slam dunk way to confirm that it's worked is to put in a new monitoring well after the application, so that any artifacts of excessive carbon moving into the well are overcome. We have done that. We have not found significant differences, and principally this is due to the fact that the PlumeStop is flowing like the water, and so the well is generally seeing what would be flowing as if the well wasn't there, which really fits the definition of a monitoring well, of how it should be, at least a formal definition of the monitoring well. There's other humorous ones too. The phenomenon of disproportionate impact to monitoring wells typically occurs if a very thin seam of carbon has found its way to a monitoring well through fracture flow and then has just packed the well or the gravel pack with carbon, with only, which then contrasts very sharply with a very thin sheet or plate or spear of a few millimeters thickness of carbon through the formation. With PlumeStop, we typically don't see that because the PlumeStop moves more like plug flow around the soil particles in the transmissive zones, such that what actually comes to the well is pretty much the same as what would be coming to the well as groundwater. That's a long answer to a simple question. The short answer is you put in confirmatory monitoring wells, and they really confirm that the monitoring well is, that there's a good correlation between the initial well and the well put in after the application. That's the most sure way to do it.
Okay, all right, thank you. We still have a couple minutes left, so maybe time for one or two more questions. Next question is, when you augment the PlumeStop with HRC or bioaugmentation, what biogeochemical performance metrics do you monitor downstream from the PlumeStop?
You're asking all the fun questions here. Biogeochemical performance metrics. Well, let me do this in two parts. Let me first unwrap this by saying that a PlumeStop project is basically a bio project under the bonnet. So the applications would be those of a typical bioremediation project if the PlumeStop wasn't there. The PlumeStop essentially is an extra component that takes the biodegradation out of the groundwater phase and onto the carbon surface. The risk is managed more rapidly and more tidily, but the destruction process is still bio under the bonnet. So ahead of the application, it would be the geochemical and biological things that would need to be reviewed are exactly the same as would be needed on a bio project: competing electron donors or acceptors, flux, mass, redox status, etc., etc. Post-application, it would be the same. We'd be looking at different indicators of the degradation. This is harder when nothing is showing in the groundwater, but we have had success looking at, using monitoring wells, just looking at quant-array tests, microbial diagnostic tests, and looking at the signature population changes of the degrading microflora, and using that as one of a number of line of evidence for the post-sorption biodegradation. In terms of the geochemical changes, then again, we'd also be looking at ensuring that the redox remains appropriate and so forth, just like a bio project. It's just that we have less to monitor with PlumeStop from the groundwater, simply because less is going in the free groundwater, less is going on in the free groundwater, and more is going on at the interface.
Okay. All right, we are just about at the end of the hour. We have a lot of questions here. We're not going to be able to get to all of them, and for those of you who need to have a hard stop at the hour, we understand. We'll send out a recording for this webinar. We have a couple more that we wanted to see if we can get answered. So if some of you want to stay on and for these last couple of questions, that's good. So just a couple more here, maybe, Jeremy. This next one here is, we got a lot of questions that were similar, like this one, or similar to it. Will PlumeStop work by itself, or is another treatment like ORC or HRC necessary?
That's an excellent question. The answer is that it depends on the site. If we're talking about, say, a large diffuse plume and low concentrations and moderate flux, then it is quite possible that PlumeStop can be used on its own. There would be two indications of when that might be the case. One is that there are already signs of the plume attenuating and it's calculated that the attenuation rate would be adequate to keep the PlumeStop bioregenerating long-term without the addition of supplemental electron donors or electron acceptors. That's often desirable because it can keep costs down. In some cases, one of our projects in Italy, for example, was one of the first of these. The plume concentrations are so low that the sorptive capacity alone is going to be 100 years or so by calculation. And the client on one particular project just elected to go with sorption alone, even though our proposal had been for sorption plus electron donor or electron acceptor. In the majority of cases, however, we will still co-apply PlumeStop with sufficient electron donor or acceptor to deal with the contamination. That's principally true in plume treatments. In barrier treatments, it's more variable how it would go about. It is attractive in a barrier treatment not to have a requirement to reapply electron donor or electron acceptor over a period of time. That period of time can be extended because so long as the degradation is greater than the influx rate, it doesn't actually matter if degradation is going on the whole time. There can be gaps between the applications, which may be a good number of years. But most of the time we'll ensure that the bioconditions, well, in fact, in almost all cases we'll ensure the bioconditions are appropriate. We're running out of time, so I'm going to answer the last question much faster.
Okay, yes, sure. Let's see here. So there's many questions that were just like this. Are there any potential regulatory issues we should be prepared for?
Let me answer that by saying that we have not yet had a project refused by regulators in the different states that we have been to. There will naturally be a lot of questions asked, and different sites will have different levels of sensitivity. In some cases there are questions such as how do we know the PlumeStop's going to stop? Is it going to hit a river? What can we do to safeguard against X, Y, or Z? There are ways of dealing with each of these points. So there have been no brick wall issues with the technology per se, but there have been a lot of site-specific questions which simply reflect prudence and good regulation for each particular case in question.
Okay, great. Thank you very much, Jeremy. We are out of time. We didn't get to everyone's question. We had a lot left, but that's going to be the end of the webcast today. If we did not get to your question, a representative from REGENESIS will be contacting you directly within the next few days to help you out. And if you need immediate assistance, please visit regenesis.com to find your local technical representative, and they'll be happy to speak with you. Thanks again very much to our presenter, Dr. Jeremy Birnstingl, and thanks to everyone who could join us. Have a great day.